Good morning, ladies and gentlemen. Welcome to PMC pre-training presentation. As you remember from last week or the week before, we started the vacuum gas oil processing block, which consists of 3 units, the VGO hydrotreater, FCC unit, and polynaphtha unit. So Pilar will take us through the slides for the FCC unit today. So as usual, we're gonna pause after each section or a slide if there is any questions or further clarification is required. So Pilar, you can start now the presentation if you hear me.
Yes. Good morning, everybody. So welcome to our online session today. As Ahmed said, last session we saw the vacuum gas oil hydrotreating unit. Today we will see the FCC unit, that is the fluid catalytic cracking unit. And next session we will see the polynaphtha unit. So what we will see today, which is the content of our presentation, we will see the FCC unit in the Carvala refinery scheme. We will see the purpose of the unit. We will see some of the unit highlights. We will see what is cracking, then what is fluidization. We will see the feedstock characteristics, the feedstocks to the unit, the products that we will get from the unit. We will see the unit yields. We will see the simplified block diagram. We will talk a little bit also about the reactor process overview, the regenerator, the main column, the gas concentration, and the flue gas system. We will talk about reactions and catalysts. We will see the heat balance around the reactor and the regenerator. We will talk about the operating variables, and at the end we will see some of the main operating conditions in the PFD for the reactor and the regenerator. So we have seen, this is our scheme for the refinery. We have seen that we receive the crude oil, two classes of crude oil. We will the BASRAF and the MISRIF. We will process in the crude distillation unit, the atmospheric crude distillation unit, and then the bottom of this crude distillation unit, we will send it to the vacuum distillation unit. From the vacuum distillation unit, we will get our VGO. This VGO, we will first hydrotreat it, and then to remove the sulfur, nitrogen, remember the other session, we have to reduce the sulfur content of this stream to 150 ppm of sulfur. And also, of course, we will remove some metal and we will have some hydrogenation of the unsaturated hydrocarbons. Then we will send this stream to the FCC unit, that is the fluid catalytic cracking unit. We will see here the capacity. We see here the capacity of this unit. Remember that the unit that we use to set the capacity of the different units, the unit is barrels per stream day. And we have the capacity for the FCC units, it is 31,500 barrels per stream day. From this unit, we will have three main streams. The main product will be a component for the gasoline pool, okay? Will be gasoline, that is our main goal, to produce gasoline. Then we will have some LPG, unsaturated LPG, that we will send it to the polynaphtha unit to produce more gasoline. And then we will have the heavier streams that we will use as fuel oil. Okay, the licensor, the technology of this unit is also UOP. Okay, so this is how is the unit in the refinery scheme. Okay, we have this, the fluid catalytic cracking. So remember, the feedstock to this unit is the hydrotreated vacuum gas oil from the previous unit that we saw last session. Remember that in the refinery, we have these main products. So our objective, our target in all these units is to maximize, in this case, the gasoline, okay, through these different units that we are placing after the corresponding hydrotreating. So let's see what is the purpose of the unit. Okay, the fluid catalytic cracking unit is where heavy, low value petroleum stream such as vacuum gas oil is upgraded into higher value product, mainly gasoline and the C3, C4 olefins streams that we saw in the scheme that we will process in the polynaphtha unit. It is one of the most important and sophisticated contributors to oil refining technology. You will see that is a fascinating technology where you will have a lot of new concepts that we will see through the unit. The FCC process has been in operation for over 60 years, during which a great deal of development has occurred. So this development have occurred in mainly two areas: new catalysts and new reactor and regenerator designs. So this is the purpose of the unit. Okay, it is to transform this low value stream, the vacuum gas oil, into higher value products, mainly gasoline and the stream containing C3 and C4. Okay, it is not a new technology, but we have seen many developments in the unit, mainly new catalyst and the configuration of the reactor and regenerator that we will see what it's about. Okay, let's see some unit highlights and then we will make a pause, a break to see if you have some questions. So the feed, first, it is pre-treated in the VGO hydrotreating unit in order to remove contaminants and improve cracking characteristics and yields. As the reaction takes place at high temperatures and in this unit, we don't have hydrogen, so the products obtained are very rich in olefins and aromatic, okay? In this case, we don't put hydrogen for the reactions. The catalyst is continuously regenerated by keeping it circulating between the reactor and the regenerator, okay? This is, I think, one of the key things of the process. The catalyst remains fluidized throughout the process. We will see also what it means. Remember that the cracking reaction is endothermic, so we will need heat for the reactions. But in the regeneration reaction, so for the coke, removal of the catalyst is exothermic, so it will release heat. So these are some highlights of the unit and the purpose that we saw in the previous slide. If you have some questions.
Guys, do you have any questions about the highlights for the FCC unit? Okay. I think you can proceed.
Okay, perfect. So we will see more about what is cracking. You know the name of the unit, fluid catalytic cracking. So we are going to see what it means cracking, and then we will see what it means fluidize. So what is cracking? Cracking involves the decomposition of heavy hydrocarbon feedstock to lighter hydrocarbons. If you see this example here, you have a long hydrocarbon here, and then you will crack in different smaller hydrocarbons. If you will crack without hydrogen, you will some double bonds here that you will form in these smaller molecules. Okay. Cracking can be carried out to any hydrocarbon feedstock, but it is usually applied for vacuum gas oil. That is our case. Cracking can be with or without catalyst. When cracking is carried out without a catalyst, higher operating temperatures and pressure are required. This is called thermal cracking. This was the principle of the old generation refinery. Okay, if you don't use catalyst, you will have to operate at higher temperatures to get the cracking reactions. Nowadays, cracking is usually carried out using a catalyst. The catalyst enables the reduction in operating pressure and temperature drastically. Okay, so as we can see, the cracking means the decomposition of the heavy hydrocarbon into lighter hydrocarbons. Okay, as we don't have any hydrogen, we will have these double bonds formed during the reaction. The reaction can be with or without catalyst. When we refer to the cracking without catalyst, we call it thermal cracking because it is mainly due to temperature. And when we use a catalyst, we will say that we are performing a catalytic cracking. Okay. We will see here also that we talk about fluid catalytic cracking. So I would like to give an overview of what is fluidization, even if this is a very specialized topic and is quite important in the industry. We will give some highlights of the fluidization. So the principle in the fluid cracking process is that the catalyst, that is a fine powder, we will see that the average size of the catalyst is about 70 microns. Okay, the catalyst. So it is a very, very fine powder. So behaves like a fluid when aerated with a gas. In this state, the catalyst can easily move through pipes and from one vessel to another. Okay, so this is the main principle of this fluidization. We'll try to explain more in details. So when a fluid flows upwards through a packed bed of catalyst particles at low velocity, the particles remain stationary. Okay, we have seen in the previous unit that we have a review that we have many fixed catalysts, fixed bed. Okay, no movement of the catalyst, because we will have, if you see this diagram at the right, we have our gravitational force larger than the drag force. Okay, so the particles will remain stationary. Okay, no movement. We don't have movement of the catalyst. As the fluid velocity increases, the pressure drop increases, and further increase in velocity creates a balance between the drag and the gravitational force. So you will start to increase this drag force until you have the balance between this drag force and the gravitational force. Okay. So here the particle begins to move. This is the minimum fluidizing velocity. This stable fluidization starts at a certain pressure drop. As the velocity increases, the bed expands and bed porosity increases. So you won't have a fixed bed, but you have the smaller particle of the catalyst floating fluidized. Of course, it depends on the velocity that you will have upwards. You will have different types of fluidization, such as bubbling, slugging, and pneumatic transport, okay? But this is a more specific concept. Maybe we will see it in the level 2 training, that inside a unit, inside the fluid, the catalytic cracking, we also will have different types of fluidization, okay? But this is only for the idea is to give you the general concept of the fluidization. We know that we need this the aeration with a gas or with a steam or with air to have this fluidization phenomena in the reactor and in the regenerator. And it's made possible that the catalyst can easily move through the pipes and from one vessel to another. Okay, this is the principle of the fluidization. Okay, that you will have this force upwards higher than the gravitational force. So you have the particle suspended in an upward gas stream. So it will move. This is the principle of the fluidization that we will see that we will have in the unit. So this was the main concept about cracking and fluidization, okay? If you have questions, or we can proceed with the fixed talk to the unit.
Any questions, guys?
السلام عليكم استاذ احمد.
السلام ورحمة الله وبركاته.
شلون الصحة؟
الله يخليك، هلا بك.
الله يخليك استاذ. العفو استاذ احمد، عندي سؤال بخصوص الفيد ستوك بالنسبه للاف سي سي. يعني مكتوب انه ممكن اني هيدروكربون يكون للاف سي سي غير الفي جي او. يعني شنو ممكن الانواع الاخرى اللي يكون ممكن نشتغلها كفيد للاف سي سي؟
اللي هو يعني انت اكيد انت تاخذ الماتيريال الهيفي، يعني كل ما يعني هيفي انت تحولها المواد من لو فاليو الى هاي فاليو، فانت تقدر اي شيء طبعا هو يدخل الاف سي سي، بس انت اذا الفيد مالتك مواصفته احسن من الفي جي او فيكون غالي عليك، فبالنتيجه ما تحقق الربحيه المطلوبه من الوحده. يعني هو انت يو كان كراك اني ثينج، يعني هو انت الغاز تقدر تسوي لك راك يتحول الى غاز مثلا، بس هل الغاز اول شيء غالي يعني مو رخيص،
يعني مثلا
هذا القصد.
الفاكيوم ريسيديو ممكن ندخل على اف سي سي؟
الفي ار طبعا هو ممكن
الى ار اف سي سي،
بس انت الكونفرجن تختلف بالضبط. مثلا تستعمل الار اف سي سي اللي هي ريزيديو،
ار اف سي سي اقوى، يعني اكثر هيفي مالته هيفير اصحاب الظروف
يستعملون مثلا الكاتاليست نوعيه مختلفه بظروف والى اخره. بس هو طبعا هو اي شيء كان كراك يعني ماكو
حد ممكن، يعني ممكن حتى الار سي ممكن يدخل مباشره يصير.
مو اف سي سي، للار اف سي سي استاذ ار وحده اخرى، بس نفس البرنسبل، يعني نفس السايكلون ونفس
هي اف سي سي بس يسموها ار اف سي سي
للار
ريزيديو. يعني انت اللي مدخله اثقل من الفي جي او، يعني هذا القصد.
بالضبط، مطروقه بالعالم كله، مطروقه
موجوده بابو ظبي موجوده بتكرير
موجوده.
شكرا استاذ سامي.
استاذ علاء تفضل.
السلام عليكم استاذ.
السلام ورحمه الله.
استاذ بس اكو نقطة ما واضحة بالنسبة لي، يعني سيجوز كترجمة ما قدرت اتخيلها صحيح، اللي هي بداية توضيح الفلويديزيشن.
التعريف يعني
إيه يعني
هذا اللي احنا
اريد ما جاي اتخيله افتهمه صحيح. يعني
هو الجواب البسيط يعني للسؤال مالتك انه انت عندك شيء صلب، مثلا عندك دقائق مال صوليد اللي هي مثل كاتاليست عندنا، صح؟ فهاي الاشياء الصلبه احنا شو نسوي لها؟ نسوي لها تتصرف كتصرف الموائع اللي هي فلويد، اللي تتصرف تصرف الموائع. ايش نقصد بها؟ السائل والغاز. فتسافر او يعني تروح باتجاه الاعلى. مثلا اذا هي بيد، اذا هي طبقه وساكنه سكون، يعني مثل ما عندك افرض تتخيل حليب وقاعد بقلاص او بكوب. فانت شو تسوي له؟ تسوي له فلويدايزيشن. اكو يا اما بالهواء، مثلا تدفع هواء من الاسفل للاعلى. فشو يصير بالباودر مال الحليب؟ يصعد لي فوق ويكون يترافل، يعني بالعربي نقول يطير مثلا، كانما طاير بالكوب. هذا التصرف اللي دا يسويه مثل الباودر مال الحليب، هاي صار فلويدايزيشن له. ما بقيته ساكن، خليته متحرك. هاي الفكره. واضحه؟
عاشت ايدك.
واضحه.
بس بينما هو يبدي صلب.
هو
بس
يبقى
احنا
لا
على
هو
مود النقله من المنطقه الثانيه.
الحاله الفيزيائيه هو ما يتغير مثلا صلب يصير سالب، بس التصرف مالته، البيهيفير مالته راح يكون بحاله الموائع اللي هو يكون فلويد، كانما غاز او سائل يعني.
عاشت ايدك استاذ، شكرا جزيلا للتوضيح.
Any more questions, guys?
Okay.
I think you can proceed. Yeah.
Okay, perfect. So let's have a look on the fixed stock to the unit. Remember that the fixed stock will be the hydrotreated vacuum gas oil from the VGO hydrotreating unit. We will have the fixed stock to the fluid catalytic cracking. These are the main specifications for this stream. We have seen that we will have this specific gravity. We have this API for the stream. Remember this factor, the UPK factor. That is a factor that it tells you how paraffinic it is your feed. It is higher, it will means that it is more paraffinic. It is lower, it means that it is more aromatic in your feedstock. And for the fluid catalytic cracking, the better feed, the best feed is the paraffinic feed. Okay. We have the sulfur content. Remember that our specification for this stream was 150 ppm of sulfur content. We have the nitrogen content that is 12 ppm. And then we have the metal content also reduced to 0.5 ppm, and also the carbon percentage, that is a measure of the coke that will produce the stream. Here we have more explanation about this factor. We will read it. Okay, the cracking of a feedstock is inversely proportional with the concentration of aromatic carbon atoms. In general, the highly paraffinic feedstock having a UPK factor of 12 gives the maximum gasoline yield. Naphthenic feedstock having this UPK between 11.5 and 11.6 give intermediate yields, and the highly aromatic feedstocks give very pure yields. Okay, so this is a factor, a calculated factor that remember that we have seen in previous session, that is calculated depending on the specific gravity of the stream and on the boiling point. Okay, so it's a calculated factor, and it will give you more or less an idea of the paraffins that you will have in the stream to the unit. So in the catalytic cracking, these paraffinic streams will give you the maximum gasoline yield. That is our target, okay? Gasoline, to produce more gasoline. Remember that all this data, you will find it in the process design basis. In this case, the FCC unit is the unit 8. So this is the document number, okay? For this process design basis for the unit 8. We'll have different products in the FCC. We will see the product that we will obtain. Here we have like the two main the sections of the unit. We have the reactor and the regeneration section that we will see more details now. And we have the main column and gas concentration unit. So we will have this of gas that we will send it to the fuel gas network in the refinery. We will have this LPG, the unsaturated LPG, that we will send to the polynaphtha to create to produce more gasoline and send it to the gasoline pool. We have our main product, that is the cracked gasoline, and also we will have these two products, these heavier products, light cycle oil and the clarified slurry oil, that is CSO, but I don't know why they put here the L. And these two heavier streams, we will send it to the fuel oil blending. Okay, these are so the main products. You see here that in the regeneration section, where you burn the coke in the catalyst, that we will see more details now, you will produce these flue gases. So the flue gas is generating from the burning of the coke in the regenerator, and we will have here a high temperature. So heat is recovered from the flue gas and is used to make steam in the flue gas steam generating package. Okay. And we have here a typical picture of a FCC unit. Okay, the reactor, the regenerator, and the main column. So these are the main products that we will get from the unit. So we have seen the feedstock and the products. Let's see a little bit more in detail some of the specifications of the products. So we will get a good gasoline with a high research octane number. We have a low sulfur content. Remember that the gasoline specification is 10 ppm, so we have a good stream for the gasoline pool. We have also low benzene concentration. So this is the main specifications for the crack gasoline that we will get from the FCC unit. Remember that also we get an unsaturated LPG stream. This is a highly olefinic stream, and we will upgrade this stream in the polynaphtha unit. Okay. And then we'll have these two heavier products, the light cycle oil and the clarified slurry oil, that in these streams, the K factor, remember that we saw the UOP K factor, or the characterization factor, they call it, or Watson factor, but it's the same definition. In this case, we have low K factor, that it means that is highly aromatic content in these streams, okay? They have high density. The cetane index is very low, so we will use it in the fuel oil blending. Both these streams we will use in the fuel oil blending. So we have seen the feedstock and the products. Now we will see the distribution of this product, what we call the yields. If we have 100 tons here, we will have 3 tons of gas that we will send to the fuel gas. We will have 21 of LPG that we will send to the polynaphtha unit. We have 57 more or less, that is a good number, of the FCC gasoline that we will send it to our gasoline pool. And then these two the light cycle oil and the clarified slurry oil that we will send to the fuel oil blending. Of course, also we have some coke formation in the cracking reactions that will be deposited on the catalyst. So these are more or less the yields of the unit, okay? For every 100, you will have this distribution of product, more or less, okay? This is to show that this is quite an important percentage of the feedstock that it will be converted to gasoline. So if you have some questions, or otherwise we will begin with the simplified block diagram description.
Any questions so far? I don't see any hand
Okay.
raised or question in the chat. I think, yeah, we can just proceed. Yeah.
Okay. So here we have the different sections of the unit. So the fluid catalytic cracking unit consists of 3 sections. That is the reactor regenerator. Okay, here you will see the reactor regenerator. Then we will have the main column section. And we'll have the gas concentration section. So we will see now the main aspects, the main description of these sections, and then we will go into more details of each of these sections. So in the reactor that you will see here, this is like the reactor, the raw oil, so our feedstock from the VGO HDT hydrotreating unit is cracked to an effluent containing hydrocarbons ranging from methane through all the hydrocarbons through the highest boiling material in the feedstock. Okay, so here we have our VGO, and here we have our product, our cracked hydrocarbons. The cracking process produces coke that remains on the surface of the catalyst particle and reduces its activity. Okay, as we have seen in other processes, the coke, that is mainly carbon, it is formed during the reactions, and it will remain on the surface of the catalyst particle, decreasing the activity, okay, reducing the activity of the catalyst, okay. In the regenerator, that is this, it is shown here, the circulated spent catalyst is rejuvenated by burning the deposit coke with air at high temperature, okay? We will see it more in details in the next slide, but the coke here with the catalyst with the coke will go through the generator, and we will here burn the coke, and we will send the regenerated catalyst again to the reactor. Okay, so this is the first section of the unit, that is the reactor regenerator. Here we have the cracking reactions will take place, and but also we have the coke formation on the surface of the catalyst. This catalyst will be go to the regenerator. We will burn the coke, and we will send back the regenerated catalyst to the reactor. Here at the top, the reaction takes place in vapor phase. So here at the top, we will have a vapor stream that it contains a lot of components of the from the reactions. So we have to go to the main column. The main column sections will separate the reactor effluent into various products through fractionation. Okay, it is a fractionation column. The overhead, the lighter components, includes the unstabilized gasoline and lighter material. The heavier liquid products, the light cycle oils, some of them will use as pump around, a strip as product for blending. Remember these light cycle oils, we will use it in the fuel oil. We will send it for the fuel oil blending. There are some side streams also here that we will see, we will use it only as a pump around for the column to remove heat. And the bottom, that we call it the clarified slurry oil, we will send it also for the fuel oil blending. Okay, so in the top we'll have our high value products, okay, that we will then separate in the following section, but also in the column we will get this light cycle oil and the clarified slurry oil that we will send it to the fuel oil. What happens with this overhead vapor? Here we will use, we have vapors and some unstabilized gasoline that we will send to the next unit. That is called the gas concentration unit. This gas concentration unit receives gasoline and all lighter products from the main column overhead and separates the mixture into the stabilized gasoline, the liquefied petroleum gas, and the non-condensable dry gas. So here we will see we have an absorption and separation process, and then we have this off gas that we will send it to the fuel gas. We have this unsaturated LPG that we will send to the polynaphtha unit, and we will have our main product for the that is the cracked gasoline for the gasoline pool. This LPG will go also through a process to remove some of the sulfur compounds, and also we'll have some, absorption for the off gas to remove the H2S. So these are more or less the three sections that we will have in the unit. An overview. Now we will go through each unit, and we will, of course, we will begin with the reactor. Okay. So here we have the reactor, okay, and here we have the regenerator. We have our feedstock is coming here, okay, that is the VGO, the vacuum gas oil. It is preheated in some heat exchangers with the taking advantage of the heat that we have in the main column. We will preheat this feedstock to the unit. So the preheated VGO and steam are introduced into the reactor riser. Let's go step by step. So this VGO and steam will go through dedicated nozzles, very specific devices, nozzles, and will enter this tube that is called riser. Okay. Why we put some steam? It is called the atomization steam for a better injection of the feedstock in the riser, okay, to create like fine droplets in the riser. Here, it will enter the feed and it will contact with regenerated catalyst and the lift steam. Okay. We have here the catalyst that is coming from the regenerator. So we call it regenerated catalyst without coke or with a very small amount of coke, because we have already burned off the coke in the regenerator. But we have also a catalyst with high temperature, okay? Without coke and very hot at this temperature that it works the regenerator. So this catalyst vaporize the feedstock, okay? And the resultant vapors carry the catalyst upward through the riser, okay? You will increase the volume, you will vaporize, and you will have the vapors in this direction. This lift steam, it is injected to improve the fluidization also of the feedstock and through the riser, okay? So remember, we have here the feed, that is our vacuum gas oil, plus some steam coming into very specific like nozzles that we have here in the riser, okay? Here is coming the catalyst from the catalyst from the regenerator. This catalyst is already regenerated, so it contains very, very small amount of carbon. And you have also this lift steam, okay? So this all will go through the riser, will see the feed and will vaporize the feed. You will have an increasing volume, so the feedstock will go through this riser, and in this riser the reactions will take place. We'll see it now. So the cracking occurs as the hydrocarbon vapors and catalysts travel up the riser. We have the hydrocarbon and the catalyst traveling up the riser. And we will have our cracking reactions here in the riser. The cracking reactions take place in only 2 to 3 seconds, required for the catalyst and the hydrocarbon vapors to reach the top of the riser. So you have the reactions in this pipe, in this riser, in only 2 to 3 seconds, okay? You have here the catalyst and the feedstock reacting. Catalyst is quickly separated from the hydrocarbon vapors to minimize further cracking reactions, okay? So when you reach here, you have here special devices that it will separate the catalyst and the vapors, that is the reaction products. And you have also here the cyclones, that are special mechanical devices that it will separate the catalyst from the vapors, okay? You don't want to go for further cracking, okay? Because then you will produce lighter components, and then you would lose some of your gasoline. So that's why we want to separate quickly the hydrocarbons from the catalyst here when you reach the end of the risers, okay? So the reactor product vapors here flow through the reactor vapor line to the main column. So here it will go to the main column. So this is the first slide of the reactor. Let's have an overview again of what happens in this section. We have our feed, that is the vacuum gas oil, hydrotreated and preheated. And we have some steam that is called the atomization steam, that it goes through these nozzles into the riser. And we have our regenerated catalyst from the regenerator, that is with less than 0.05% of coke, and at this temperature, very hot catalyst coming here, and some lift steam to help with the movement and fluidization of the catalyst. So this very hot catalyst, it will see this feedstock that it comes 200 and something, we will see now degrees, and will vaporize this feedstock, and will travel together in the riser, and catalyst and hydrocarbon will will go through the cracking reactions. Okay, so it will go through the riser, and here at the top you will separate the catalyst from the vaporous hydrocarbons. Okay, you will use special devices to separate the catalyst from the vapors. Okay, during the cracking reaction, a carbonous byproduct called coke is deposited on the circulating catalyst. Okay, we have our cracking reactions, but also we have the coke formation on the catalyst. So here at the top we have vapors, our product in the vapor phase, and we have the catalyst with coke. The catalyst, referred as spent catalyst, drops from the reactor chamber into the stripping section, whereas counter current flow steam removes some adsorbed hydrocarbon. So the catalyst will goes in this direction through this stripper, okay, where we inject steam to remove some adsorbed hydrocarbon. Okay, we don't want hydrocarbons in the catalyst, so we will strip the hydrocarbons with the steam. The stripped catalyst flow to the regenerator, where the coke is continually burned off. So we have here in this line the spent catalyst. So we have seen the reactor. This is the overview of the reactor. Okay. You have your regenerated catalyst coming into the reactor, going up with the feedstock. It will separate it here, the catalyst will fall here, will go to this stripper to remove the adsorbed hydrocarbon, and will go to the regenerator. Okay, so this is the flow of the catalyst is in this way. Okay, and it's in continuously flowing through the regenerator to the regenerator. To the catalyst with the coke, okay, and we call regenerated catalyst the catalyst that is coming from the regenerator. You can see here also that the reactor temperature more or less is 532 degrees. Okay, as we have seen, these reactions that take place here, it requires heat. We have endothermic reactions, and we have here exothermic reaction, that is the combustion of the coke in the catalyst. Okay, so this is more or less what it happens in the reactor. Let's see now the regenerator, and then we can have the questions. So in the regenerator, the heat of combustion raises the catalyst temperature to this level, more or less 707 and 709 degrees C. The purpose of the regeneration is to reactivate the spent catalyst so that when the catalyst is returned to the reactor riser, it is in the optimum condition to perform its cracking function. The regenerator serves to burn off coke from the catalyst particle and transfer heat to the circulating catalyst. The energy carried out by the hot catalyst is used to vaporize and heat up the oil vapor to the desired reaction temperature in the riser. And the hot regenerated catalyst also provides the heat reaction, okay, necessary to crack the feedstock to the desired conversion level. We will see later the definition of conversion. So the hot regenerated catalyst is accelerated with this lift steam before contacting the feedstock. So now we have seen the overview of this reactor regenerator, okay? So here in the riser, we'll have the cracking reactions, and then we have here the catalyst, the spent catalyst. Why spent? Because we have coke, we have lost some of the activity of the catalyst due to the coke formation. Then the spent catalyst will flow through this pipe to the regenerator. Here we will introduce air and we will have the combustion reactions, okay? Remember that the combustion reactions will release heat, so we will have this temperature. So we will have here catalyst with very low amount of coke and very hot catalyst. Of course, as we have a combustion reaction here, we'll have some flue gases, okay, from this regenerator, okay? These flue gases are hot, and then we have seen in the previous slides that we will take some of this heat to produce steam. We will see later when we will talk about this flue gas section. Here also, you see that we have these mechanical devices that are the cyclones. The idea is that you don't have a catalyst in the flue gases, or at least as you remove as much as possible with these cyclones, that it will recover most of the catalyst. We have here special distributors for the air, for the combustion air. And also you just can see here that you have to continuously withdraw some of the catalyst that we call the equilibrium catalyst. That is the catalyst that has been in contact with the feed and has been through the unit. And we will put some fresh catalyst to maintain the activity of the catalyst. Okay. Whereas we can see here, we see here also that we have these valves. They are very important valves that it will control the amount of catalyst, the spent of catalyst, and the amount of regenerated catalyst to the reactor. How it will control this catalyst going to the regenerator or going to the reactor, mainly due to two controllers. This valve will act with the level control in the reactor, okay? Remember that this is like a fluid. It is in a fluidized state. So you will control the liquid, the level control here with this valve, and this valve will be controlled with the temperature in the reactor, okay? Why with the temperature? Who gives the temperature to the reactor? The catalyst. So if you want more temperature in the reactor, you will have to have more catalyst here to heat your reactor, okay, to have more temperature. So these are very important valves in the system. We'll have 3 types of steam. We will see it. We have this steam that is used to strip, for stripping the catalyst, to remove some of the hydrocarbons that could be absorbed on the catalyst. We have this steam that we call the atomization steam that is injected with the feed in the special nozzles. And we have here the lift steam, okay? Also, where this is more or less what I wanted to talk about this section that is the most important section of the unit, which is the heart of the unit, when we have the reactor and the regenerator. So if you have questions, please.
Guys, any questions about the reactor and the regenerator and what's happening in those two equipments, the FCC unit? Don't see any questions, so I'm assuming everyone understands exactly what's happening here.
Or no? No.
Yes,
we have two choices.
Either they don't understand the or they fully understand.
Okay.
Yes, they have a good information about FCC.
That's good.
Okay.
Because them trainer they are very good specialists.
That's what we'd like to hear.
Okay.
So you can proceed there.
Okay. So this is our first section. This regenerator and the reactor. So here you see that we get our products from the reactor that we have to send to the column, okay, for the separation of the different products. So the product vapor from the reactor flows to the bottom of this main column. You see here the vapors going to the column. The column overhead, that it will consist of unstabilized gasoline and gaseous olefin-rich co-products flow to the main column condensers. Here, okay, we put only what heat exchanger, but we have an air cooler and a cooling water condenser, okay? And then here we have our reflux drum. Here in this receiver, in the main column receiver, you see that we have a vapor phase and we have a liquid phase. This vapor phase will go to the gas concentration unit. It will go to the compressors, okay, the wet gas compressors. And the liquid phase, it will also go to the gas concentration unit, but it will go to the primary absorber, okay? And part, of course, we'll use as reflux in the column. Remember that we saw that also in this column, we have the light cycle oil and we have the clarified slurry oil. The light cycle oil is recovered as a side-cut product with the net yield being stripped for removal of light ends and sent to the further processing or storage. Okay, we have this stripper like we had in the atmospheric distillation column to remove the lighter components, and then we can send this to the storage and we will use as fuel oil, this light cycle oil. We see here that some of the heavier streams will use only as pump around in the column, okay? Here also we have some streams that goes to the concentration unit for heating and then comes back to the column. And here, the bottom of this column is the clarified slurry oil that also will send to storage for the fuel oil blending. So we'll take advantage, of course, of this heat. Remember that I told you that the feed to the reactor is preheated with some streams from the main column. So these are the heat exchangers, okay, that we will use to heat the feed to the reactor. That's why we saw that we have the preheated raw oil or the VGO to the reactor. Here is where we heat the feed, okay, in this heat exchanger from the main column streams. So it is important to see that we have the vapors from the reactor here at the bottom of the column. Of course, our main product will be the lighter products in the top of the column. Here in the top of the column, we will condense, and the liquid that we have here is the unstabilized gasoline that we will send to the absorber in the gas concentration unit. And the gases, of course, we will try also to recover as much as possible the valuable products in this gas stream. So we'll send to the gas concentration unit and will be compressed in the wet gas compressor. And then we will have this side stream from the main column process, from the main column. So now we have, I don't know if you have questions or if you want to make a break, Ahmed, I don't know.
Yeah, that's a good idea actually. We can come back half past.
العفو استاذ احمد، اذا ممكن سؤال قبل.
تفضل استاذ.
سؤال بس بالنسبه للهيفي نفثه، ليش انا ما اوديها للسي سي ار وممكن استفاد من عندها؟ ليش جاي اوديها للغاز كونسنتريشن وارجعها مجرد بس استفاد كتبريد وبمقرها من عندها؟
الهيفي نفثه انت هسه صار عندك يعني غازولين بس توخر السلفر اذا اكو سلفر منها.
لا هو حاليا الهيفي نفثه مجرد يوديها للغاز كونسنتريشن تبرد ويرجعها للمين كولوم.
يعني شنو تقصد، رفلكس ولا البرودكت؟
لا هو اكو خط.
اسمح لي هسه انت هسه تكون عندك الغازولين بس هو انستابلايزد.
اوكي تمام. انا
بس اسمح لي
تمام
سوي له ستابلايزيشن وخلص عندك انت صار برودكت غازولين بعد. وين اشعل يا
اوكي هذا لا هذا الغازولين طلع ويا التوب.
زين
اوكي اكو خط تحته موجود الهيفي نفثه، هذا ما يصير لي شيء، مجرد انا اوديه للغاز كونسنتريشن
زين
استفاد من حرارته وارجع للمين كولوم فقط. يعني اذا تلاحظ ان الخطين جوا الهيفي نفثه تو غاز كونسنتريشن يونت وبعدين يروح للغاز كونسنتريشن يونت ويرجع مجرد للمين كولوم.
تمام. على هذا الراجع شنو الكويستشن بالضبط؟ ليش
هذا شنو؟ ليش انا مو هذا هيفي نفثه ما ممكن اني اوديه مثلا
يقول لك ليش ما اوديه كانتاج استاذ احمد، اوديه للسي سي ار اسوي غازولين.
Pilar, you know the stream, the second stream from the right hand side, the heavy naphtha from the concentration is back to the main fractionator. So the question is why we are sending this stream back to the main fractionator rather than send it to, for example, CCR.
Yes, because these are like uses like internal streams in the column. It only gives some heat and comes back to the unit. No?
Yeah, so this is the same idea of pump around in the
yes.
fluid distillation unit. So this is distillation column.
Yes.
So what you provide cooling to the top, plus it's like improve your fractionation in the main fractionator. أستاذ مرتضى سمعتني؟ أستاذ مرتضى؟
وياك أستاذ أحمد.
أي فيعني أنت هسه الفكرة
ما جانا الصوت.
تسمعني هسه لو ما تسمعني؟
استاذ احمد الصوت راح
واضح.
بالاجابه، هسه يسمعك.
نعم.
اوكي. الفكره هذا هو صحيح انت تشوفه هيفي نفثه وكانما برودكت طالع تقول ليش رجع من فراكشنيتر، بس مثل لو تتذكر بالكرود ديستليشن كولوم كم بامبر راوند عندنا، فنفس الفكره نفس المبدا مال البامبر راوند هذا هو، بس المقطع مال هيفي نفثه، فهذا ضروري انه يرجع للفراكشنيتر. اول شيء
هو هنا الغرض منه بم اراوند، بس ما ممكن يعني
بالضبط مو الفكره، بس اسمح لي، الفكره مو انت تنتج هيفي نفثه من هذا المقطع، يعني انت الغرض من هاي تسميه الهيفي نفثه الجايه من الكونستريشن يونت او سكشن اللي موجوده بالاف سي سي، هذا يرجع للمين فراكشنيتر اللي هو شنو هو؟ ازاله اي حراره اكيوميليتد بالتور ويحسن الفراكشنيشن ويبرد. يعني تفهم القصد؟ نفس المبدا مال البامبر راوند
بالضبط. فشي يمتص لك المواد الثقيله اللي صاعده ويا الغازات.
هو تبريد،
يعني هاي هم فائده، يمتص تبريد وامتصاص تقريبا.
بالضبط.
الشغلات الخفيفه اللي صاعده ويا الغاز، لان الهيفي نفث لها طبيعه الامتصاص مذيبه. يعني راح تنقي لك الاوف غاز اللي صاعد هو والال بي جي.
تمام.
اوكي.
شكرا استاذ.
تستفاد من عندها كمصدر امتصاص يعني كمذيب، اضافه للتبريد. يعني هي لان تبردها حتى تصير فعاليه الامتصاص ازيد كل ما تبرد الهيفي.
هو انت يعني مو انت هذا شنو اذا انت ما تسويها ايش راح تاثر؟ تاثر على الهيت بالانس الموجود بالتور، فبالنتيجه هذا ايش راح ياثر؟ ياثر لك على الفراكشنيشن، يعني انت تجزئ، انت تريد تجزئ المقاطع اللي موجوده بالبرج التقطيع، فبالنتيجه هذه كلها الافشنسي مالتك تتاثر. فيا اما تصير الطبقه العليا اللي انت مثلا كميه الليكويد المفروض موجوده تكون جدا قليله فتصير دراي، فالبالانس كله يتاثر. فلذلك عندنا احنا خطوط البامبر راوند يعني تتحسن بتحسن كبير كميه
الكواليتي
فراكشنيشن. انت مو انت تسوي، انت تسوي تقطير يعني، فعمليه التقطير عندك تحسن البامبر راوند. اوكي استاذ علاء، كان عندك اتصور شفت رافع ايدك.
استاذ بس سؤالي انه بخصوص الكلاريفايد سلوري اويل قاعد نسوي اي نعم اللي يطلع من البوتم، قاعد نسوي له اكسشينج ويا الرو اويل، هذا منين قاعد يجينا بالاضافه طبعا للكولينج ووتر؟
يعني الرو اويل منين يجينا؟
اي نعم اللي قاعد نسوي له هنا منين يجينا مباشره من ستوريج من غير وحده؟
اوكي خليني اسال بيلار، بس هو الفيديو.
Yes.
Pilar, the raw oil, you mean the VGO, right?
Yes. Yes. You know, sometimes they call it.
Feed.
So in the feed to the reactor, we will see that we have like a different heat exchangers. We will where we will heat the feed to the reactor. So these are some of the heat exchanger. Okay. You see here that you see only one side of the heat exchanger, but the other side is the raw oil or the feedstock, no?
Yeah, so we've got a question from Miss Hibe saying, what's the purpose of the reflux of the light cycle oil and the clarified distillery oil? So if you answer that one also.
Yes, this is also to have the proper traffic inside the column. Okay, like the pump arounds in the main distillation column. Remember that this is like the fractionation column, but it's not equal. Here we have vapor. We don't have you don't have any other heat to the column. You have the vapor from the reactor coming in, and you have coolant here the vapor. So this the way they have designed it to have the proper traffic inside the column, no? The liquid vapor inside the column.
Yeah. Okay. ست هبه هو نفس المبدا البامبر راوند. احنا شنو اللي يصير؟ انت على كل تري موجوده اكو كميه من الفيبر اللي تغادر التري، واكو ليكويد اللي موجود عليه. نحافظ على فد ليفل معين اللي موجود اللي هو الوير اللي يحبس السائل بنسبه معينه على كل تري. فعندنا بالانس موجود هيت وماس على كل تري. فاحنا لغرض نحصل عملية الفصل المواد اللي بداخل برج التقطير يحتاج لنا حراره معينه، فالحراره بدون البامبر راوند تصعد تصير كلش عاليه، فالحراره الموجوده بداخل برج التقطير بدون التبريد اللي جاي بسبب البامبر راوند الحراره تصير عاليه، فبالنتيجه شنو؟ المقاطع اللي المفروض يطلع منها منتج بالحاله السائله كلها راح تصير شنو؟ تصير في الحاله الغازيه، فاحنا هذا ما نريده. ليش؟ هذا راح كله ياثر على عمليه الفراكشنيشن، يعني مو كان ما يطلع لنا غازولين، ايش راح يطلع لنا؟ راح يطلع لنا بس غاز. ليش؟ لانه ما عندنا كولينج بالبرج، فكل افكار الرفلكس هي للتبريد. التبريد وبالاضافه الى تحسين عمليه التقطير. فلذلك احنا شنو اكو بكل مقاطع عندنا برودكت معين، اذا ماكو عندنا بامبر راوند وتبريد المقطع المفروض بيسال يصير كله غازي، فبالنتيجه ما يطلع سائل، يطلع بخار، يطلع من الويذدرو مالتنا. فهذا كالمبدا اللي هو نفسه موجود بالسي دي يو يعني. اوكي let's see if we have further questions. Yeah, مستر حسين تفضل.
السلام عليكم أستاذ.
السلام ورحمة الله وبركاته.
Good morning, Mrs. Pillar.
Hi, how are you?
Ms. Pillar, you already say we have cook formation about 5% in the product.
The coke, no?
Yeah.
Yes.
After burning this cook, we produce off gas about 3%.
We produce flue gases.
Yeah.
Yes.
I mean, in the end, my question, in the end, how much exactly we have coke in percent? Is 5% minimum?
No, we have 5% of yield for every 100 tons that you will have with feed. You have around 5 tons of coke in the catalyst. Okay, but it will also, you have to take into account the catalyst that is flowing in the unit, no, to make the calculation.
Yeah,
But
I mean after burning.
After burning,
and produce flue
yes.
gas, we have 5%.
No. After burning in the catalyst, do you have less than 0.05% of coke in the catalyst? Okay. But this 5% is the yield if you take into account the feed to the unit. But if we will see also that we have in the same basis something that they call the delta coke, that is the coke in the regenerated in the spent catalyst minus the coke in the regenerated catalyst. Okay.
Yeah, that's okay. Thank you very much.
Okay.
Do you have more questions, guys? Okay, so I don't see more questions. So we can break, I think, 30 minutes if you want.
Okay, perfect.
So yeah, 30 minutes. Yeah. Okay, so see you in 30 minutes time.
Okay. So we have seen so far the reactor and the regenerator, and also the main column process overview. So we have seen that we have our product from the reactors going to the column, and here in the column, in the fractionation column, we get these two streams. We get one gas stream from this accumulator, and we get this liquid stream.
Yeah, no, it's good.
Now it's good. Okay. So I was telling that remember that from the reactor we get our vapors, that we have our products here in the reactor vapors. So we go to this fractionation column with the idea to separate them, the product from the rest of the streams. So in the top we have this accumulator where we get this gas that we will send to the gas concentration unit, and we will send also this liquid to the gas concentration unit, but to different places. This gas will be compressed, and this will be sent to the primary adsorber. And we saw also that here we have some side stream that we just do like pump around to the column to recover some of the heat and to go back to the column. So the next section that we will see is the gas concentration unit. We saw that we will send here net gas and liquid. So the net gas from the main column section is compressed and cooled before entering the stripper absorber system. So we have here our wet gas from the main column receiver. It is compressed. We have a wet gas compressor, 2 stages, and we cool in the high pressure condenser. The liquid we will send to the high pressure receiver. The gas from the high pressure receiver, referred to rich gas, contains valuable products in the propane-butane range. So the gas is washed with cracked gasoline, unstabilized gasoline from the main column overhead receiver to recover this product in the primary absorber that we will see now. Remember that the idea of this gas concentration unit is to recover as much as possible our valuable product from the column. So the gas from this high pressure receiver, it will enter the primary absorber. So we will have liquids flowing down and gases going up on the primary absorber. What kind of liquid we will have here? The unstabilized gasoline, that is the liquid from the accumulator in the main column that we see. This is our unstabilized gasoline that we will go in the primary absorber. Also, we will use some of our product, of the final product, the stabilized gasoline, in the top of the primary absorber, okay, to improve, to recover more the C3 and C4, okay? So we will have 2 liquid streams coming into the absorber. The unstabilizer from the main column overhead, remember the liquid portion, and the FCC gasoline that is part of our product coming here to recover more C3 and C4. From the primary absorber, the gases from the primary absorber, it will go to the sponge absorber. Here, always the idea is to recover as much as possible the valuable products from our stream. So the sponge absorber is a packed tower where any remaining C5 plus material is removed by contact current contact with a lean oil, specifically the light cycle oil from the main column section. Remember that we have the light cycle oil in our main column, so we will use part of this light cycle oil, like lean oil here, to recover as much as possible this C5 plus material that we have still in this gas stream. Okay. So this is the idea of this first part. We will continue now with the other part of the gas concentration unit. But remember that the idea is to have these absorptions. Okay, here, remember absorption is favored by high pressure. So we'll have this absorption in the primary and in the sponge absorber. Here we will use the unstabilized gasoline. That is our main product, but still unstabilized. And also a small amount of gasoline, our product. And here we will use as liquid the light cycle oil from the main column section. So after that, the gas from the top of the sponge absorber is sent to a lean gas amine absorber. Remember that we usually use amine to absorb H2S. So remember the sponge absorber that we saw in the last slide? We send it to this amine absorber. Okay, remember that this off gas will go to the fuel gas system, and we have to have a specific value of sulfur content in this off gas. Okay, so that's why we have this absorption here with lean amine before sending this off gas, the lighter components, to the fuel gas system. The rich oil from the primary absorber contains not only the desired C3 and C4, but also some lights and some H2S. Okay, so we are now talking about this stream, okay, the liquid from the primary adsorber. It contains our product, final product, but also it contains some lights and some H2S. So it will go here, it will go to this high pressure receiver. These components will be removed by charging the high pressure receiver liquid to the stripper. Okay? So we have to send the liquid coming from here to the stripper to remove the light components and the H2S. So we will send the liquid to the stripper. The stripper vapor will return to this high pressure condenser and high pressure receiver. And here, of course, the gases will enter again to the primary adsorber. Okay, so here we have removed the H2S and the lighter components from our stream from the high pressure receiver. But still we have to separate the LPG from our gasoline. So the stripper overhead vapor returns to the high pressure receiver condenser from which the lighter gases again enter the bottom of the primary adsorber. And here we have our debutanizer that we will have our product in the overhead will be the polynaphtha, the 3,3,C4 stream, and here we will have our gasoline. Okay, here this LPG before going to the polynaphtha unit is processed for the H2S and COS removal. Okay, it's a caustic wash and some amines also treatment in the unit. So this is the gas concentration unit where we have two main streams coming in. That is the wet gas from the main column receiver and is the unstabilized gasoline also from this receiver, but the liquid part of the receiver. Okay, so here we compress, here we go to the primary adsorber, then we go to the sponge adsorber. Here we have the lighter components that we will send as fuel to the fuel gas system. And then here we will have the debutanizer that we will have as an overhead product, our LPG that will go to the polynaphtha unit. Remember that this stream is highly olefinic stream that we will send to the polynaphtha unit. And here we have our gasoline, that is our final product that we will send to the storage for the gasoline pool. Okay, so the idea, as you can see, is to recover as much as possible the valuable products and to have, of course, the lighter components that we'll have to send to the fuel gas system. If you have questions about the gas concentration unit, okay. So remember that you can stop me whenever you have a question. I will try to stop after each section. Okay. Remember that we have in our regenerator the flue gases from the combustion of the coke. We had the flue gases. These flue gases has the composition. We will have water, oxygen, nitrogen, CO2. We'll have some SOx, and we will have some catalyst. I have not said, but we will see also later that this regenerator goes to the complete combustion. We don't have CO here in normal operation. We don't have CO, but we will have CO2. Okay, So in this regenerator, remember that we have the cyclones to remove as much as possible the catalyst, but we will have still here some catalyst fines in the flue gases. Remember that these flue gases will have very high temperature that we can take advantage of this heat to produce the steam. So the flue gas exits through the regenerator cyclones to minimize catalyst entraining prior to discharge from the regenerator. Remember that at the end, the flue gases will go to the atmosphere through the stack. So we have to minimize the catalyst in these flue gases. The sensible heat of the hot flue gas is recovered in a flue gas steam generator. We have here this box. We will introduce the boiler feed water, high pressure boiler feed water. We will have also the some saturated steam that we will produce in the main column bottoms, and we will produce saturated steam, and then we will overheat, superheat this steam, and we will get superheated high pressure steam. Okay, so this is a way to recover some of the heat of these flue gases to produce high pressure steam in this flue gas steam generator. Remember that this temperature was around 700, that is the temperature in the regenerator. The catalyst lost from the regenerator is removed from the flue gas stream by the electrostatic precipitator to reduce the flue gas catalyst fines prior to venting to the stack. Okay, this is the idea of this electrostatic precipitator, to remove the catalyst fines that we have here in the flue gases prior to send the flue gases to the stack and then to the atmosphere. The SOx here in these flue gases, we have a limit, okay? For environmental reasons, we cannot have a lot of SOx in these flue gases. And even if we work with a hydrotreated feedstock, we will have some SOx. How we will reduce this SOx here? We will use an additive, okay? We will use a desox additive that we will introduce with the catalyst, and this catalyst, this additive, excuse me, will transform the SO in H2S. Okay, remember that then we can remove this H2S in the gas concentration unit with the amine absorption. Okay, but this is an additive that we will see later also in the PDF that we will add to transform SOx into H2S. Okay, so to comply with the SOx limit, a desox catalyst additive is used. When the desox additive is circulated to the reactor, the SOx is converted to H2S, which afterward exits with the reactor effluent, reducing the SOx emission from the regenerator. Okay, so this to comply with the maximum amount that we can have here of SOx. Remember that this SOx can, if you vent it to the atmosphere, it is also a cause of the acid rain. So this is a flue gas system overview. So if you have some questions.
Okay, let's check.
Sorry, Mrs. Bilal.
Hi.
What is the difference? What can we use catalyst fine?
The catalyst fine is the smallest particle size of the catalyst, okay?
Yes. Can be reused?
We have some catalysts, we need to have some catalysts fine, but we cannot reduce and we cannot recover the 100% of the, even using the cyclones in the regenerator. Always we will have some loss of catalyst in these flue gases.
I mean, after electrostatic precipitator, it is fine.
I don't know if you will use here, but I suppose we'll,
Dilar, he said if we could use it again, this fence. Maybe it couldn't. We couldn't use it again.
yes, we could use it, and we couldn't mix it with the fresh catalyst to the regenerator. But I don't know how much catalyst you will recover here in if it's valuable to inject again in the system.
استاذ واضح استاذ الجواب لو لا؟
واضح استاذ. شكرا.
Okay, okay.
Any more questions, guys? Okay, yeah, you can proceed. No more questions.
Okay, let's see an overview of the reactions that take place. We have seen that we have the cracking reactions. So, but you can imagine that a complex series of reactions take place when a large gas oil molecule comes in contact with a high temperature catalyst. The distribution of product depends on many factors, including the nature and strength of the catalyst acid sites. We have two kinds of reactions. We have the primary cracking of the gas oil molecules, and we have the secondary rearrangement and recracking of cracked products, okay? So the primary cracking reactions, more or less, these are the main reactions that take place in the riser, remember? That we have the catalyst in contact with the feed. We'll have the paraffins. This is the formula for the paraffins, the alkanes, converted to paraffins plus olefins. We'll have olefins cracked to smaller olefins. We'll have alkyl aromatic side chain scission. Okay, if you have an alkyl here with an aromatic, you will have the aromatic plus an olefin. The naphthene cracked to olefins, and we don't have aromatic reactions, okay, in this kind of the fluid catalytic cracking reactions. So remember, we have seen that as we don't have hydrogen here, we will produce a lot of olefins from our reactions, okay? So the compounds of lower molecular weight are produced caused by cracking of hydrocarbons, okay? If you see here the molecular weight of this, and then you will have these smaller molecules here, so you will have lower molecular weight products. Remember, quite important, that all these reactions are endothermic reactions, okay? They need heat to proceed. There are accompanied, of course, we have coke formation on the surface of the catalyst. So high boiling, low octane number feedstock are converted to low boiling, high octane number products, okay? This is the objective of the unit, and this is what you will get through these reactions. As you can see here, we are transforming for 1 mole of this hydrocarbon to 2 moles in the other side of the reactions. So these reactions take place at low pressure, okay? These cracking reactions. Also, of course, we will have the secondary reactions. There are not so desired reactions, but it will take place. when an aphthine will react with an olefin, will produce an aromatic plus paraffins. With an hydrogen and olefin will produce a paraffin. Also, a normal olefin can go to an isoolefin. And of course, we'll have these reactions that will transform this aromatic plus olefin into coke. Okay, that this is the multi-ring aromatic compound that is the coke that we will burn in the regenerator. So we have our primary reactions and we will have our secondary reactions. So it is important, remember, to separate the catalyst from the vapors from the reactor after 2-3 seconds and avoid secondary or recracking of the product because it will produce lighter components or components with lower octane number. How do we get these reactions? Remember that we have said at the beginning that we are in a unit and a catalytic cracking. So we need to use a catalyst. We need to use a very specific catalyst to get our gasoline products. The FCC catalyst nowadays has 4 major components, okay? We have a zeolite, we have a matrix, we have a binder, and a filler. We will see what it means each of these components. The zeolite is the primary active component of the catalyst, okay? And the zeolite used in the FCC catalyst is referred as type Y, okay? We see here the zeolite. This is the primary component of the catalyst that we will use in the unit, okay? And here we will represent it with this square. This is our zeolite. You know, this is a very sophisticated structure in the zeolite. The catalyst site in the zeolite are strong acids and provide most of the catalytic activity, okay? Remember that the zeolite provides most of the catalytic activity. Then we have the matrix component that contains alumina, amorphous alumina, which also provides catalytic activity sites and in larger pore that allows entry for larger molecules than those the zeolite. So the zeolite has smaller pores than the matrix, okay? The matrix alumina that is represented here by this yellow, okay? So we have the matrix component, it is mainly alumina, also provides catalytic activity sites, and it has larger pores than the zeolite. Then, of course, we have another component that is the binder and the filler that provides the physical strength and integrity of the catalyst. The binder is usually silica and the filler is usually clay. So we have our 4 components of the catalyst. We have the zeolite, we have the binders here, you see here, this like joining these two, the clay and the zeolite, and we have also this matrix. Okay, and here of course the pores of the catalyst. So we have all these in very, very small particles. Okay, so this is the catalyst that is used in the FCC, and we will see that this catalyst is quite a small catalyst, like a very fine powder. If you see here, we have the catalyst, okay? Of course, we have different sizes, but the average of the catalyst is about 70 microns, okay? So you can imagine it's very, very small particles. Okay, usually, okay, we have our catalyst supplier. We will send some samples of the catalyst. Remember that we saw in the regenerator that we withdraw some of the catalyst that we call it equilibrium catalyst. And we will send regularly some samples of the equilibrium catalyst to the catalyst supplier, okay? For them to evaluate the activity and the performance of the catalyst. We will also need to add fresh catalyst to the unit, okay? To maintain the desired level of activity and to make up for physical losses, okay? Remember that we are losing some catalyst in the regenerator. Even if we have the cyclones, we will have some, lose some catalyst. And of course, we withdraw some equilibrium catalyst. So we will have to add fresh catalyst. Usually, there will be a minimum daily catalyst makeup rate of between 1 and 2% of the catalyst inventory, according to the operating manual of the unit. Also, this is another figure that what is expected by the licensor, by UOP. It's a makeup catalyst consumption that is equivalent to 0.07 kilograms of catalyst per barrel of feed. Okay, this is the makeup expected by the licensor. So this is the catalyst, as you can see, very, very fine particles with a very characteristic composition with 4 major components that we have seen in the previous slide. It is added continuously fresh catalyst to the unit to keep the activity of the catalyst, okay, that is circulating through the reactor and to the reactor, okay. So this is all about the reactions and catalysts. If you have some questions. Okay, then you can make also questions later at any moment. Okay, after the catalyst, we wanted to show what is important in this unit. Remember that we have said that we have 2 main reactions. One is the cracking reaction, of course, in the reactor that consumes heat. It is an endothermic reaction. And we have another reaction, and the important one also, the combustion reaction of the coke that releases heat. So we have here the heat balance of the unit. We don't have any external heat that we will add to the unit. So we'll have this balance across the unit in the reactor and the regenerator, okay? So the combustion of the coke is exothermic, that produces a large amount of heat that is partially absorbed by the regenerator catalyst, which in turn provides further heat required for the vaporization of the feedstock and the endothermic cracking reactions that take place in the riser. This makes this unit, the fluid catalytic cracking unit, a largely heat balanced system. You see here, you have the feed, the lift steam, you have the stripping steam, the reactor vapor. Of course, even if you have a very well isolated reactor and regenerator, you will have some radiation losses. Okay, but the idea is you have a heat balance here. The heat that will provide this catalyst will serve to vaporize the feed, to also to heat the different streams coming to the reactor, and will provide the reaction heat. Okay, the cracking reaction heat that it is required for the reactions to take place. Okay, then of course we'll have some heat content here in our product, and in the regenerator also remember that we have some heat here that we will use to produce steam. Okay, so it is all well balanced, the heat in the unit. And of course, we will make some examples maybe in the next level. When we see the more details about the unit, we will make a heat balance in the reactor and the regenerator. Remember that you will have a lot of data for your system, temperatures, flows, and then you will be able also to make this calculation during the running of the refinery, the operation of the refinery. So I don't know if you have questions about this heat balance. It is important that to understand this, because in the next section also we will talk about the operating variables. And as you can see here, if you change some of the temperature here, or you change the temperature here, that you want more temperature here, it implies a lot of changes in all the system, okay? Because it's a heat balance system. So any change that you will make in one of these variables, for example, the temperature here, if you decrease the temperature in the feed, you will have to add more catalyst, because you will have the heat provided, you will need more heat provided by the catalyst. So it will impact also the spent catalyst that you will send to the regenerator. So as you can see, any change that you will perform in one of the variables that you can adjust, it will imply a lot of consequences in the rest of the unit. So we will continue with the operating variables. We will make also some definitions of conversion. So let's begin. When we talk about cracking severity, if you hear someone talking about cracking severity, it means increase in cracking conversion, okay? So, but you will ask, what is conversion? We will see now. Feed conversion is adjusted, regulating the operating variables accessible to the operator, okay? We will see now also what it means, these operating variables that you can manipulate, okay? A change in a single operating variable causes one or more other operating variables to change, as we have seen. And this is a direct consequence of the thermal balance, by means of which the energy produced by the coke combustion is transferred from the regenerator to the reactor. Okay, so we are going to talk about operating variables. We are going to define this conversion. Okay, and remember that whenever you make a change in a single operating variable, it will cause a lot of things downstream in other variables to change, okay? Because due to the thermal balance that we have around the unit, okay? Let's define conversion. Conversion is a measure of the degree to which the feedstock is cracked to lighter products and coke during processing in the FCC. How do we calculate conversion? We have our feed, and we will have our light cycle oil and our clarified slurry oil. Okay, so feed minus light cycle oil minus clarified slurry oil divided by feed multiplied by 100, it will give you the percentage of conversion. If you see here, remember the yields that we saw in the previous sections, you will you produce also coke and your product. So the feed minus the heavier compounds, in fact, you are calculating the amount of the feedstock that is cracked to lighter products and coke, okay? Using this formula. LCO, remember light cycle oil, that we see this a stream from the main column that we will use in the fuel oil system, and the clarified slurry oil, that is the bottom of the main column, that we will also use as fuel oil, okay? This formula, you can use it in volume or in weight. This is when we see some of the design basis, we will see this conversion corrected. Okay, we have some true conversion that we will have correct for the gasoline boiling point, okay? But we will try to explain later, okay? But this conversion, as it is calculated, as you see it here, is called as an apparent or as produced conversion. The catalyst oil ratio also, it is an important operating variable. This is the ratio of kilograms per hour of catalyst circulated to kilograms per hour of fresh feed. This is not an independent variable. You cannot adjust it, but you will adjust some other variables that will tend to increase or decrease this catalyst to oil ratio, okay? But it's not that you will put a number and then you will have, no. It will be a consequence of other operating variables. This catalyst to oil ratio will increase if you increase the reactant temperature, and decreases with higher regenerator or feed temperatures, okay? When process conditions are changed so that an increase in the catalyst to oil occurs, also we have an increase in conversion, but also we have more coke, okay? So this is another definition also that you will see in your operating manuals, another variable that is the catalyst to oil ratio. That is simply the ratio of kilograms per hour of catalyst that you have circulating in the system divided by the fresh feed. So let's now define what is called the independent and dependent variables, okay? The independent variables can be adjusted by the operator, okay? You can adjust the temperature of the reaction. You can adjust the preheating temperature. Remember that we have seen that we have the VGO preheated before entering the reactor. Just so you can adjust this temperature. You can adjust this recycle flow rate, but we will see that in normal operation, we don't have any recycle. We will can adjust this activity, and we can adjust this combustion mode, that in our case is a total combustion. So these are the variables that can be adjusted by the operator, and we call it independent variables. The dependent variables not directly accessible to the operator but adjustable via independent variables. We have the regenerator temperature As we have seen, now we have the catalyst circulation flow rate, the conversion, and the combustion airflow rate, okay? So we have independent and dependent variables, okay? So we will focus more now in these and independent variables. We will see the definition of these variables, and we will have an overview of the effects on the dependent variable when we move one of these variables, okay? Let's begin with the reactor temperature. Remember that here we have our feed, the riser, the temp, and the reactor here. We can adjust this temperature. How? How will we adjust this temperature? Who will provide the heat to the reactor? Who is providing the heat to this part of the system? The heat is provided by the regenerative catalyst. Remember that here we have the catalyst without coke or almost without coke, and we have hot catalyst, okay? Very hot catalyst. So the reactor temperature is the prime control of the reactor severity or conversion, and is set to obtain the desired conversion and gasoline octane number. It is already fixed, more or less fixed by the licensor according to the feed characteristics. It is okay, you have to work at this temperature more or less to get your desired products. So it is controlled by adjusting the regenerative catalyst to the reactor. So this valve, okay? We'll adjust the valve if we want more temperature. If we increase the set point here, it will open more this valve, okay? That is the regenerative catalyst to the riser. So some of the consequences, if you increase the temperature, you have more catalyst circulation, you have more regenerating temperature, more conversion, have production of C3, C4, and dry gases, and other effect in other variables, okay? But remember that any change that you make in an independent variable, it will have effect in other dependent and independent variables. Here we have the main consequences if you increase the temperature. But the important thing here to remember is that you control the temperature of the reactor by manipulating this valve, okay? So if you want to decrease the temperature, you will close this valve. If you want to increase the temperature, you increase here the set point of this temperature, it will open this valve, okay? Remember that we have said that this valve is controlled by this temperature control, and the other valve here, the spent catalyst valve, it is controlled by the level control here in the reactor, okay? Well, so we have the temperature controlling this and the level controlling this, okay? Another variable, it is the preheating temperature. We have our feedstock from the vacuum gas oil hydrotreating unit. We have like a source drum, and then we will go through different heat exchangers. Remember that we have seen these heat exchangers in the main column. One is with the light cycle oil, with the clarified slurry oil, with the other and the other side streams. Okay, so we will preheat the feed from around 207 degrees to 259 degrees C. . If we decrease this temperature, okay, because here we have a temperature control where we can bypass some of the feed, so we can decrease this temperature. We will have to increase the catalyst circulation, okay? Because here we will have to have more heat to the feed, okay? So remember that the heat is provided by the catalyst. So if we need more heat, we will have to increase the circulation of the catalyst. So we will have to open more the catalyst circulation to the reactor. So this is another important variable, that is the preheating temperature, okay? You can control here in the last heat exchanger, you have like a temperature control where you can bypass some of these feed to this heat exchanger, or you can pass all the feed through the heat exchanger, and this will affect the catalyst circulation. As you can see, all the variables are interconnected. If you change one, you will have two. Some of the dependent variables, you will have also a modification on those variables. The recycle rate, it is defined by this formula, okay? In some cases, you will have some recycle from the column to the reactor, but in normal operations, you don't have this recycle, okay? So the recycle to the riser is not necessary during normal operation. So this recycle will be 0. So this combined feed ratio will be 1. Okay, we will see that is also one of the design variables in the unit. Okay, so we don't have this recycle, so this is 0, and we will have this CFR as 1. This recycle will be used during turn down or when lighter feedstock are being processed, okay, to help the unit heat balance. But in normal operation, and we remember that at this level of the training, we talk about normal operations, okay? We are not talking about startup or shutdown of the unit. So during normal operations, we talk that this combined feed ratio is 1. The other variable that we can handle is the catalyst activity. This catalyst activity requires a very good management of the catalyst inventory for a smooth operation. Okay, as we have seen before, we have the equilibrium catalyst, that is the catalyst that have been in contact with the feedstock that is circulating in the system. We should remove some of the equilibrium catalyst at regular intervals. And of course, we'll have to add some fresh catalyst. Must be added to the unit to maintain the desired level of activity and to make up for physical losses. Okay, so here in the regenerator, we will perform this catalyst management. We will draw some of the catalyst, the equilibrium catalyst, and we will add some fresh catalyst. And then we will keep the activity of the catalyst. This addition of the fresh catalyst should be made as continuously and evenly as possible, okay? So this is another important variable where you can add, okay? Because you will have the responsibility to have this good management of the catalyst to have a proper catalyst activity. We call it equilibrium catalyst to the catalyst here that is already been in the process, and fresh catalyst, that is the makeup catalyst, that is the new catalyst, okay? Remember that we have seen that other independent variable was the regenerator combustion mode. We will see here some of the definitions of the combustion, the partial and total combustion. So coke is a mixture of carbon, mainly carbon, some hydrogen, which when burned in the regenerator can produce carbon dioxide, carbon monoxide, and water. These are the reactions for the combustion of the coke, okay? Of the carbon in the coke. So we have if we have a partial combustion, the second row, we have carbon plus oxygen, and we have CO plus heat. If we proceed with the combustion of this CO plus oxygen, we will have the CO2 plus heat. So if we see the complete combustion will be C plus oxygen, so carbon plus oxygen, giving CO2 plus heat. That is a complete combustion. The carbon burning may be complete or it may be only partial to a CO and CO2 mixture. And carbon monoxide may in turn burn to CO2 and achieve maximum combustion. If the unit is operated for total combustion, the maximum amount of heat is released, resulting in the highest catalyst temperature. We want a hot catalyst, so it is better to have a total combustion. If we compare the heat that is released during the complete combustion, it is this amount, okay? That is 7,863 kilocalories per kilogram of carbon if you have a complete combustion, while partial burning to CO yields only this amount of heat, okay? So you will see that it's a big difference if you go to partial or if you go to a complete combustion in terms of heat release during the combustion. So in the Carvala FCC unit, the high efficiency regenerator is designed for complete CO combustion. How we will get this complete combustion? We have to adjust, of course, the air rate to the regenerator and maintain an excess of oxygen in the flue gases, okay? The excess of oxygen, it is recommended to have between 1 and 2 volume percent excess of oxygen in the flue gases. We'll see now when we will see the process flow diagram that I put some numbers, and I remember that according to the material balance, this oxygen in the flue gases is around 1.7, okay, in the process flow diagram. So remember that we have this regenerator for a complete combustion. We will have more heat, and we will have the catalyst with very high temperatures. And we have to maintain this excess of oxygen to have the complete combustion. Okay, that is an important also variable that you will have to handle when you are operating the unit in the refinery. Okay, the airflow to the regenerator. Okay, these are the main operating variables that I wanted to show you. Now I will show you the PFD with some of the conditions that we have seen, and also some of the design, we will see some of the operating conditions according to the design basis for the unit. Here This is taken from this document from the process design basis, the same document that we saw before. Is that you have some of these process design basis for each unit in the refinery. This is for case 1. Remember this combined feed ratio definition? It was 1 plus recycle divided by feed, but we don't have recycle in normal operation, so this combined feed ratio is 1, okay? This is the vacuum gas oil preheated to the riser. That is, the temperature is 274. Remember that is preheated with some heat exchanger and with some streams from the main column. So we reach this temperature in the preheated raw oil that we call it, or VGO to the riser. The reactor temperature, it is 532. We have the pressure. Remember that we have seen that in this kind of reactions, we produce from 1 mole, we produce 2 moles of product. So these reactions are favored by lower pressure. So we are working at low pressure at 1.4 kilograms per square centimeters. We have here the steam that we have to put into the riser. That is a weight % of the fresh feed. This is more or less 4%. Here we have more or less the catalyst circulation. Remember that this is not, you will not fix it, but this is a consequences of the other independent variables. We have here the delta coke. Remember that before we talk about this delta coke. This delta coke is defined as the coke in the spent catalyst minus the coke in the regenerated catalyst, and it is about 0.7 weight %. We have here also the temperature in the regenerator. Remember that we have seen also when we were talking about in the process description, it is about this level of temperature that we will get in the regenerator. This is the air that we will have to add per kilogram of coke, dry air, okay? Here we have this that is not applicable in our case because we don't have CO. Remember that we are going to a complete combustion, okay? This is the conversion, already the true conversion corrected, okay? We'll see maybe in the other training and the other level how to correct this conversion. It is converted as is for the 94% point of the gasoline distillation at 193, but maybe we have our 90% at other temperatures, so we have to correct this conversion, okay? But well, it's a set of formulas that we have to use according to the gasoline that we will produce in our unit. So these are the main operating conditions of this section, of course, of the reactor and regenerator, okay? I would like to show you the PFD if you have some questions, or we can have the questions whenever you want.
Thanks, Pilar. FCC unit, there is a question, I think, from Ms. Hib. FCC unit designed for complete combustion, but if partial combustion happened, what will be the effect and change?
So if you don't have the complete combustion, you will have an implication in all the heat balance of the reactor, no?
Yeah.
Because you have less heat in the catalyst, and you will have to adjust all the unit operation, no? But according to the manual, the normal operation is going to complete combustion, okay? Adjusting the air to the regenerator So you will ensure that you have enough oxygen to go to the complete combustion.
That's fine. Yeah. Plus, you lose the heat.
Yes.
The heat and source. I mean, it will be affected, so you will get less heat required for the reaction if the combustion is complete, right?
Yes.
As we've seen, the kilocalorie per each 1 kilogram will be reduced drastically.
Yes.
Okay.
Yes. Yes.
Okay. Any more questions?
أستاذ أحمد. بس بالنسبة هو الريجنريشن كومبشن مود.
أي.
تسمع؟ إذا هو مصفى كربلاء مصمم إنه هو complete combustion mode، أنا ليش أعتبره هنا هو variable؟
لا، هو مو موضوع variable، بس أقصد يعني إذا ما صار incomplete لسبب ما، مثلا هو عندك يعني الريكوايرد صار أقل أو لسبب ما، يعني إذا نقول شنو، فالسؤال كان شنو التأثيرات لو إنه عندك incomplete.
لا سؤال منفصل أقصد أنا، هو هنا الوحدة مصممة تشتغل complete combustion mode. تمام. زين أنا ليش أعتبره هي هذا متغير بهاي الحالة إلا إذا كان ممكن ألجأ للبارشل كومبشن مود؟ مو صح هيك يعني؟
لا
في حالات أقدر.
هو ما أدري يعني هسه أنت تحكي على كم اوبريتنج مود. أنت normal operating condition complete combustion. So you have CO equals to 0. That's it.
That's it. Yes. And how you will why we say that this is an operating variable? You have to adjust the air, the combustion air, and of course you have an analyzer of the oxygen and the flue gases that it will tell you if you are having an excess of oxygen to ensure your complete combustion. Okay, so you can adjust the airflow to the regenerator.
واضح استاذ مرتضى؟
واضح تمام.
لانه انت اقول لك يعني هو او بشكل عام احنا حتى من نقول ستادي ستيت او الديستليشن كولوم مالتك ستادي ستيت، هو ماكو شيء اسمه ستادي ستيت، يعني كلها فاريبلز هي.
هو اقسم هو من يقول لك يعني اوبريتنج فاريبل معناها انا اقدر اتحكم بيها.
هو طبعا تقدر تتحكم بكميه الهواء اكيد. هو تغير يحتاج لك استقرار للوحده يعني. هاي الاشياء يعني احنا من نقول مثلا فاريبل او مو فاريبل، وحتى المو فاريبل هو تراد لك وقت يلا تستقر يعني، خاصه مرحله الستارت اب.
تمام. زين عفوا استاذ احمد، بالنسبه للاكتيفيتي اوف كاتاليست يعني الاوبريتنج يسيطر عليها عن طريق الاكوليبريم كاتاليست والفريش كاتاليست ميك اب.
احد الطرقين طبعا، الطرق الرئيسيه هي هذه. ليش؟ لانه انت وين راح تبين عندك باليلد والاكتيفيتي مالتك تبدا تقل، فيحتاج انه تبدل او تضيف فريش يعني وتسحب. ليش؟ لانه
معناه اقصد يعني بنقول المشغل هو يسيطر على اكتيفيتي اوف كاتاليست اللي هو ديبندنت فاريبل. المقصود هو يسيطر على كميه الاكوليبريم كاتاليست وكميه الفريش كاتاليست. هيك مقصود.
صحيح، هذا التاثير
بالتالي يسيطر على كميه على اكتيفيتي اوف كاتاليست.
الكونفرجن اي طبعا بعد، بس انت هاي وين هاي كلها تاثر على الانتاجيه مالتك يعني.
تمام. استاذ احمد ممكن الويت كومبريسر
شلون؟ العفو. كومبريسر
الويت كومبريسر اللي نستخدمه بهاي الوحده.
اوكي. الويت كومبريسر
يعني احنا نعرف ان الكمبريسر ما يصير يدخل لها ليكويد. زين هنا شلون بهاي الحاله الكمبريسر نقدر نسميناه ويت كومبريسر؟
Pilar, so why we call it wet compressor if you remember the reason?
Because we have from this some of the components that we will recover in the absorber, no? But exactly why wet, I don't remember.
Okay, yeah, it doesn't. I think it does not mean you have a liquid. So
No.
There is no two phase. So yeah, that's why the misunderstanding happens. So what it doesn't mean you have water or liquid in the inlet.
No.
That's impossible. Yeah.
Yes, we hope.
اوكي استاذ مرتضى، يعني ما عندك
واضح
تقدر تشيك على
يعني المقصود مو بها تو فيس.
لا بس هو مثلا يجوز اكو نسبه معينه مثلا من بخار الماء مثلا او رطوبه مثلا، تقدر تشيك بس تشيك الهيت ماتيريال بالانس مال اللاين الداخلي يعني. شوف التركيب مالته يعني ايش قد الكميات الموجوده.
شكرا استاذ منون.
Okay. Any more questions? If we go back, one of the questions, if we go back to slide number 30, what's meant by radiation loss? Okay. Pilar, you want to answer? You don't need to go back.
Okay. Well, remember that even if you have very well insulated this equipment, you have some losses of heat through the walls of the reactor and the regenerator. So it is a percentage that you will assume during the heat balance calculation. Okay, very small, but you will assume some heat losses.
Yeah. استاذ علاء ما اعرف اذا واضحه، بس الفكره انه انت حتى اذا عندك انسوليشن وانسوليتد الاكويبمنت فاكو نسبه من الاشعاع نتيجه الحراره العاليه اللي عندك اياها اللي فوق ال 500 مئوي، فيصير عندك حراره مفقوده يعني. هذا المبدا الاساسي يعني. حتى انت اذا عندك عزل اكو نسبه من الحراره تفقدها للجو. هاي الفكره. اوكي.
قصدي استاذ انه احنا مخلينها فد اتجاه انه فد ستريم او شيء للحراره المفقوده، يعني
لا لا لا
شيء
مو
يمتص هاي الحراره المفقوده.
لا 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 مو هذا القصد. انت هسه معده عندك، اذا اي معده تشوفها تحتاج حراره للتفاعل او تحتاج حراره للبروسيس، وانت عازلها، حاط فايبر جلاس وعازلها. رغم العزل اكو حراره. انت اذا تتقرب من المعده وتخلي ايدك على العزل حار، صح لو لا؟ هاي الحراره صحيح. هاي مفقوده للجو. هي هاي الفكره يعني. او الفرن هسه اذا انت شايف الافران اللي موجوده اكو عزل واكو يعني ما تريد تخسر الحراره اللي نتيجه الاحتراق بداخل الافران، بس تشعر بالحراره من تتقرب من المعده، صح ولا لا؟ هاي تعتبر راديشن لوس اوف راديشن. هاي المعنى مالته.
تمام، يعني هذا السهم اللي كان موجود انه فقط للدلاله انه راح يطلع عندنا لوس راديشن،
مو عندك ستريم طالع. لا لا يعني الفكره انه عندك حراره يعني كحراره مفقوده نتيجه العزل. ماكو عزل 100% يعني.
انا توقعت انه عندنا فد شيء
لا
انه قاعد نخسره بسبب الراديشن وقاعد يطلع.
لا بس كمفهوم يعني المفهوم العام.
عاشت ايدك. واضح.
Let's check what happened. This one we've done that one. I think that's it. Yeah. So you can show your.
Yes, I will show you in Paint because then I can have.
Oh, okay. Yeah,
okay.
Yeah.
Okay. So this is the PFD. You are seeing, no, the PFD here.
Yeah.
The PFD of the reactor regeneration section for case 1. So let's begin with the feed. Okay, the feed, it's here. Okay, I am putting the arrow here at the top of the right. Okay, here it is the feed preheated. Okay, and we have the temperature that is 274 degrees C. Remember that we heat this feed with the heat exchanger with the streams from the main column. Let me use better approach. Okay. Here we see the main characteristic of the feedstock. We have a molecular weight. If you see here, let me put it bigger. The molecular weight here, we have 346 kilograms per kilomole for the feedstock. Okay, here 347 more or less, and here we have the flows of the feedstock. We go to the reactor. Okay, that is here, the reactor that operates more or less at these conditions, and we have in the top our products. Okay, the reactor vapor to main column. Okay, here we have, this is the stream 200. If you go to your material balance and you go to this stream 200, you will see that the molecular weight of this stream is 64. So you can see that from the molecular weight that we had in the feed, that is our vacuum gas oil, that was almost 347, we go down up to 64. So this is due to our cracking reactions. We will go to lighter components, okay? That is the importance of this unit in the refinery, okay? To go from these very heavy hydrocarbons to lighter hydrocarbons. Also, I have shown here the different steams that we have in the reactor. So the steams that we have in the reactor, we have the stripping steam, remember here, the stripping steam that goes to the reactor, and we will strip some of the adsorbed catalyst and hydrocarbons in the catalyst. We will have also the atomization steam that will enter with the feed here in this pipe with the steam will enter with the feed to the riser. And at the bottom of the riser, we have the lift steam, okay? That will help with the fluidization in the riser. Of course, here we have the riser, okay, which is here the riser, okay, here in red, in the middle, okay. We have the top of the reactor going to the column, and we have the catalyst. We will show as black the catalyst flowing here down, okay, and here we have our cyclones that will separate the catalyst from the vapors. We have here the catalyst going to the stripper, okay, through this side of the reactor. It will find the stripping steam, and then we'll go through this line, okay? That is the spent catalyst line. You see here above, that is this Q102, that it will control with this level control, okay, in the reactor, okay, as we have said before, okay. So here we have the spent catalyst going to the regenerator. In the regenerator, we'll have this air in green, the combustion air, going to the regenerator. Okay, the combustion air flowing here to the regenerator and making the combustion of the catalyst. Here we have also the cyclones, okay? We show in green here at the top of the regenerator. The idea is to remove catalyst from the flue gases, okay? And at the top of the regenerator, remember here we are in the regenerator. At the top, we have the flue gases. That is the stream 164 here. And we have here this amount of oxygen. Remember that we have said that we have to ensure between 1 and 2% volume of oxygen in the flue gases. In this case, we have 1.74, and we have this temperature 714 degrees C. Okay, so we have an excess of oxygen to ensure the complete combustion in the regenerator. So the regenerated catalyst that we have here in purple will return to the reactor. Okay, through this line will go to this reactor. Here we have this other valve, very important valve, that is the 08Q101, that it will be regulated by the temperature control in the reactor. If you see here in the reactor, in the vapor line, you see here the temperature control acting on this valve, okay? That is the regenerated catalyst to the reactor. Remember that this catalyst contains very low amount of carbon, of coke, less than 0.05% weight of coke, and it's quite hot. Okay, so it will vaporize our feedstock and also will provide the heat for the reactor. Okay, so this is mainly the regenerator. What else we can see here? At the left, we see here this like hoppers. We have the equilibrium catalyst. Okay, in this like a tank. Okay, TK 102 equilibrium catalyst, and we have the fresh catalyst. Okay, so this is how we will manage our catalyst to the in the regenerator. We will withdraw some equilibrium catalyst and we will add fresh catalyst. Okay, this is more or less the where we have all these catalyst management. Also here you can see, let me put it in orange here. This additive, this is a package. Remember that we have seen that we inject some additive in the catalyst. Here we have this package, the 08PK002, where we add this the soak additive. The idea of this additive is to transform any SOX in H2S because we don't want to have SOX in the flue gases. Okay. Well, this is more or less what I wanted to show. We have a lot of things here in the PFD, but these are the main operating conditions. Okay, remember that at the bottom of the PFD, you will have the streams with the main operating conditions. Okay, here we have the stream number, temperature, pressure, and weight flow. And if you want to find a more characteristic of the stream, you go to the heat and material balance, and you will have all the detailed composition of each stream of the unit. Well, this is more or less, if you have questions about this PFD.
Let's check, yeah, thanks, Pilar.
You're welcome.
Any questions, guys? Yes. Mr. Hussein, yes.
Yeah. I have a question about the cyclone equipment. Why in the regeneration section we have 2 stages of cyclone, and in the reactor we have just 1 stage? Not effective enough or what?
Yes, you want to ensure that you don't have this catalyst in the flue gases, no? But there are, I think that these are different sizes of also of cyclones. I haven't seen the set details of the cyclones, no? But you have to ensure here that you will not have particles of catalyst here, and also in the reactor that we don't see it, but there is another disengager here when you finish the riser. There is another mechanical piece that will make like the first separation of the catalyst from the vapors. Okay, that is here, but of course we cannot see here all the details, no? But we have here like some disengager that will make like a first separation of the catalyst and the vapors, and then you will have the cyclones.
Okay, another question about the cyclone. You see the cyclone number 101. We have A, B, C, D, E. That means we have 5 packets?
Yes, we have these 6 cyclones here and these 5 cyclones in the reactor around the reactor.
Yeah, this is about as a spare cyclone or it's work all in parallel or in series?
No, I think that I haven't seen the data sheet, but it's in that.
The confusion, I think the confusion is
No,
because
the cyclone is core, one core. It's one core.
the confusion is
5-1.
coming from the PFD. The PFD does not depict
No.
the reality. So this
No.
sheet is just one direction, but actually the cyclones is distributed on circumference.
Yes.
So it covers the whole space
Yes.
inside the reactor. يعني بشكل دائري كامل then يفترن الستة.
واضح.
Yes.
Okay, thank you.
Yes, it covers all the area.
Yeah.
Yes.
That means that this charge is not just 1 point. It's about 5 point or 6 point.
Yeah. You
Yes.
disengage in every single direction. Yeah. Try
Okay.
to get rid of the problems. Yeah.
No, it's clear.
Any more questions?
بس استاذ احمد بالنسبه للستريبنج ستيم في خط يعني هو اللي يستخدم من الاسفل الرياكتر على مود ينزع عنا الهيدروكربونات اذا موجوده ويا الكاتاليست، بس اكو خط من فوق اذا ممكن. هذا
الاول واحد
هذا اللاين 108 تمام، اللاين 128
128 stream number 128. yeah
Yes.
128 there is
اللي فوق اذا هو
no 128 you mean no if you go up pillar.
Yes, we have different places where to inject this steam.
Yeah.
The total is this 191 stream.
That's right. So what's your question? Sorry, what's this?
هذا الستريبنج ستيم هنا اللاين 188 الغرض مالته واضح. زين هذا اللاين ال 128 اللي طالع لي فوق هسه الصوره تنزل شويه
128
تمام.
You are at this?
بس
yeah, the top yeah.
Yes.
So 128
the top, you know, the vessel V102, yeah.
Yes. This is also they say in the operating manual that this is like a Porsche steam. Okay, this is to avoid any coke formation in this part of the reactor. They also inject some steam in the dome of the reactor. So you have a lot of points where you inject the steam in the along the reactor. No? But this is the idea also to decrease the possibility to have coke formation in this part of the reactor.
Okay.
Okay, thank you.
You're welcome.
More questions, Shabab?
Mr. Ahmed, we have two questions in chat channel. Could you please check it?
Chat, I don't see any question in the chat. Let me check again. So if we no, I don't see any question in the chat.
اكو اثنين استاذ احمد، اكو سؤالين بالشات واقف خل اشوفهم.
ما ادري بدي اشوف اخر واحد على موضوع الراديشن لوس، هذا اخر شيء.
لا FCC Unit design for complete combustion, but
yes.
if partial combustion happened, what will be effect unchanged?
We did
second one, if we
did answer.
Yeah, we answered it, yes, before. If we go back to the page number 13.
We did that. We did.
Okay. This is the chat. I'm reading the chat.
Yeah, the chat, from Mr. Ala Rahim.
Yeah.
We did answer.
Yeah.
No, that's not
we answered. Yes, not a new one. Old one.
Now we ask about new ones now.
Yeah.
Any more questions? I don't see any more questions so far. So I think that was very useful, especially marking up the PFD just to give.
Yes, I feel like